Okay, good day everyone. Welcome back to our discussion on graph theory. In the previous video, we discussed the overview of the problem where we want to find the fastest route or the shortest path from a starting point to destination. And we saw that this is just one of the applications of a branch of mathematics known as graph theory. Graph theory is a systematical study of relations between objects. The objects are represented by small circles, and the relation between them are represented by line segments. Now, the relationship between objects could be one way or two way, depending on the problem or what is being studied. And then finally, um, we also discussed the history of graph theory, which dates back 1700. Now, in this video, we discuss some preliminary concepts for graph theory, which are vital in solving the problem, the shortest path problem. So let's continue. By an undirected graph, what we mean is a graph consisting of vertices, these are the small circles, and edges, these are the line segments joining two vertices. Now we draw undirected because this means that the relationship between vertices are two-way. Vertices U and V are adjacent if they are joined by an edge. This edge is denoted by UV. So for example, this is the vertex U and this one is the vertex V. Then this line segment joining them is UV. Now we can also refer to this as VU because the relationship is two-way. Now let's take a look at this example. Let me erase the drawing. Let's take a look at this example and let's call this graph G. For our graph G, notice that we have 5 vertices, 1, 2, 3, 4, 5, and we have 1, 2, 3, 4, 5, 6 edges. So in particular, this edge is AB or BA. So this one is our vertex set and this one is our edge set. Now, we differentiate the order and the size of the graph. By the order, this simply means the number of vertices. On the other hand, size is just the number of edges. So going back to our previous example, we have vertex set A, B, C, D, E and edge set AB, AC, BC, CD, CE, and DE. So notice that the number of vertices is 5. This one is the order. And the number of edges is 6. This one is the size. Okay. Now let's continue. Now we differentiate or define multiple edges and loops. If there is more than one edge joining two vertices, then G contains a multiple edge. So for example, this is the vertex U and this one is the vertex V. So if there are more than one edge joining them, what we have is a multiple edge. Okay, let me erase that one. Now, how is it different from loop? So when we say loop, it is an edge from a vertex U to itself. So to draw, for loop, you have a vertex, say U, and you have an edge from U back to itself. So this one is a loop. So let's take a look at this example. So notice that vertices D and E are joined by 3 edges. So this is an example of a multiple edge. On the other hand, vertex A has a loop. So this defines multiple edges and loops. Now let's differentiate multigraph and simple graph. If a graph contains multiple edges or loops, at least one of these, then we say that the graph is a multigraph. Otherwise, the graph is simple. Now let's go back to our two previous examples. Which between the two is simple and which one is a multigraph? So as you can see, G is simple because it doesn't have multiple edges or loops, whereas H has a loop. It also has multiple edges. Therefore, this is a multigraph. Okay. So in our discussion of determining the shortest path or the fastest route from a starting point to destination, we will restrict our discussion on simple graphs. Okay, let's continue. Now we define the degree and neighborhood of a vertex. So when we say degree of the vertex, denoted by this symbol, it is the number of edges that are incident to the vertex U. If the vertex U has degree 0, there is no edge attached to it. If it is degree 1, there is one edge attached to it. Degree 2, two edges. Degree 3, and degree 4. Now, closely related to the concept degree is the neighborhood. The neighborhood is denoted by n of u. This is the set of all vertices that are adjacent to u. In other words, the neighborhood of the vertex u is the set of all neighbors of the vertex u. Now let's go back to our simple graph, G, and let's take a look at vertex C. Now, which vertices are neighbors to the vertex C? Notice that C has neighbors A, B, D, and E. So we have the neighbors of C, A, B, D, E. We don't have to specify the graph. And the degree of the vertex C is 4 because it has 4 neighbors. Okay, next. Now, it is important to understand walking on the graph as this will be needed when we go to finding the shortest path or the fastest route from a starting point to destination. A walk of length k from vertex v0 to vk is a sequence v0, v1 up to vk of vertices such that two consecutive vertices are joined by an edge. So this means v0 and v1 joined by an edge, v1 and v2 joined by an edge, until vk minus 1 to vk joined by an edge. We will denote this walk by this sequence. So let's take a look at our simple graph G. Okay, now let's illustrate the walk CBACE. So you start from the vertex C, then you go to B, then A, and then back to C, and then E. So that is our walk. And I have this animation to um, show the walk CBACE. So C to B is there, A to C, C, going back, oops. So you have C to B, B to A to C, and C to E. Okay. Now, we will have two different types of walk in this discussion. We will have a path and a cycle. Now, when we say path, we mean a walk such that the vertices in the sequence are all different. Whereas a cycle is a walk such that the vertices are different except the first and the last. So let's illustrate this in our previous example. Now the walk A, B, C, D is a path. Okay, so what we do is you start from A, you go to B, C, and then D. So you have this path: A to B, B to C, C to D. Okay. On the other hand, A, B, C, A is a cycle. So you have A to B, B to C, C to A. So you formed a cycle in this case. So in this example, you have a cycle of length 3. Now let's go focusing on our simple graph G. Is it possible to have a cycle of length 4? Please comment below for your answers. Okay, so let's continue. Now we differentiate connected graph and disconnected graph. Basically, this is self-explanatory. A graph is said to be connected if there is always a path from a vertex to another. This means that you can always have a path from any vertex, any starting vertex to any destination vertex. Otherwise, the graph G is disconnected. Let's take a look at this graph. It has 14 vertices and they are already numbered. Okay. Now, why is this graph disconnected? Please comment below for your answers. Okay. So in our discussion in this video, we will restrict our graph to simple graph and connected graph. Again, we will restrict our graph to simple graphs and connected graphs. Okay, continuing our discussion, we have the notion of a weighted graph. So what is this weighted graph? We say that a graph is a weighted graph if all the edges are assigned with numerical values. Now here are some examples. So the vertices are the small circles, the edges are the line segments. Notice that there are no directions, so these are undirected graphs. Now the numbers on the edges could represent the length of the road in between them. It could also represent the time it would take to travel from one point to another, or it could also represent the transportation fee, okay, from one point or one vertex to another. Okay, so there are many uses of weighted graphs, and for our discussion, we will treat these numbers. The weights are either the distance between the two vertices, or it could also mean the time it takes to travel from one point to another, or it could also mean the transportation fee from one point to another. So for our discussion, we will restrict our graphs to simple, connected, and positive weighted graphs. So negative weighted graphs will not be discussed in this course. So far we have discussed relations that are two-way. What about relations that are one-way? For relations that are one-way, we have the so-called directed graph. A graph D is directed if it consists of vertices V of D and arcs. So instead of edges, you have arcs. So the arcs have arrows. So you can tell the starting and the destination. that are formed using ordered pairs of vertices in VD. An arc from U to V, written bracket UV, and in this case, we call U the initial vertex. So this is the starting vertex, and V is the terminal vertex. So here is an example. Oh, by the way, the notion of order and size is similar to the notion of order and size in undirected graphs. So let's take a look at this directed graph. Notice that 1, 2, 3, 4, 5, 6 vertices. So the order is 6. And we have 1, 2, 3, 4, 5, 6, 7 arcs. So notice that here, one can travel from 1 to 2, but cannot go from 2 to 1, as the relation is just one way. So in our case, if there are one-way streets, we can treat them as directed graphs. So this ends the preliminary concepts that we need in order to solve the problem on determining the shortest path from a starting point to destination, or the fastest route from starting point to destination. For the next video, we will now discuss how to solve these problems.